Thank you so much. That was a piece called Money Talks by my father. Next, we'd like to play a composition called The Seven Song. So you'll hear some interesting things from Karthik. He's got a huge line of percussion instruments. This piece is called Seven Song.
Okay. Brother, can you increase the track for me? And reduce the violin for me, please.
Tatang, tak tatang, tak tatang, kritik tadi. Tatang, tak tatang, tak tatang, kritik tadi. Tatang, tak tatang, tak kritik tadi. Tatang, tak tatang, kritik tadi. Tatang, tak dadim. Tatang, tak kritik dadim. Tatang, tak dadim. Tatang, tak dadim. Tak dadim. Tak dadim, tak dadim, tak dadim. Tak dadim, tak dadim, tak dadim.
Very simple. What Ambe did is called Konakol. Let's all try it together. Ta, ka, di, na. Ta, ka, di, na. Takka, dinna, takka, dinna. Takka, dinna, takka, dinna. Taka taka dina dina, taka taka dina dina. Dina dina, taka taka dina dina, taka taka. Taka dina, taka dina dina, taka dina dina. After this, you can join the Subramaniam Academy of Performing Arts, and I'll try to teach there. The art is called Konakol.
That certainly set the energy for this evening. We'll have more of them later. Well, they say curiosity killed the cat, but the cat had 9 lives, or did it? Well, good evening, and on behalf of all of us at the Infosys Science Foundation, warm wishes to every one of you at the start of this new year, and welcome to this evening's program, the Infosys Prize presentation for 2025, a year that marks 100 years of quantum science research, and hence the cat. I am Deepak Padaki from Catamaran Ventures, and I'm delighted to be your host again tonight. A very special welcome to our chief guest this evening, Professor Randy Schekman, Nobel Laureate and Professor of Molecular and Cell Biology at the University of California in Berkeley. May I also extend a very warm welcome to his partner, Professor Sabiha Merchant, who is here with us today and incidentally was a member of our life sciences jury a few years ago. So welcome, ma'am. May I now request Mr. K. Dinesh, the president of the Infosys Science Foundation, to lead our chief guests to their seats on the stage. Thank you. Well, tonight we gather in the presence of 6 luminous minds, researchers whose work spans multiple disciplines but are unified in their journeys, not merely one of academic pursuit, but a quiet act of faith, where the unknown is the goal and the very process of discovery leads them into uncharted territory, a belief that beneath the surface lies a deeper truth, an order waiting to be revealed. And in a time when outcomes are demanded instantly, these scholars embody a very different rhythm, one of patience, of disciplined curiosity, and a deep commitment to pursue questions whose answers may lie far beyond the horizon and ultimately lift society. More specifically, in India, a nation that is shaped by ancient inquiry and youthful ambition, supporting fundamental research is an investment in our own unfolding story and our belief in the human potential. And to set the tone now with his opening remarks, I'm very pleased to invite the president of the Infosys Science Foundation, Mr. K. Dinesh.
Thanks, Deepak. Now I'll start my formal speech to all of you, few words, but I also have in the end an exciting news that you all may want to know. Which one do you want? I'm sure you want me to finish the formal one. I'll start with that. Good evening, Happy New Year to our chief guest, Professor Randy Schekman, Professor Sabiha Merchant, esteemed jury, Infosys Prize laureates, fellow trustees, and all the invitees. Welcome to the Infosys Prize ceremony, the most awaited event to start the year in high spirits and with great hope. The Infosys Science Foundation takes great pride in celebrating emerging researchers whose work reflects the evolving strength and promise of science today. We extend our heartfelt congratulations to the winners of the Infosys Prize 2025. Please give them a big hand. Even louder. That's good. The work of these 6 young winners shows a promising path towards a more sustainable and resilient world. Be the work of physical sciences winner using renewable energy for chemical synthesis, or insights into very essential DNA repair work that our life sciences winner has undertaken. In economics, our winner shares new ways of looking at market design that could increase the efficiency to match donors and seekers of organs, or even match candidates and colleges better. From the use of holomorphic maps by our mathematics winner to the study of optimization and use of dynamic and efficient algorithms in contemporary engineering and computer science, balanced with the study of ancient languages, Prakrit or Kannada, in the humanities. See the variety of things they have done. Amazing. We all know the benefits of science extend far beyond the confines of academic institutions, touching lives in tangible and transformative ways. To ensure we all reap the benefit of this work, we need to foster meaningful research collaborations across borders. Towards this goal, we instituted the Infosys Prize sabbatical program, inviting our winners from outside India to spend a month with Indian institutions to exchange ideas and share knowledge. We also aim to inspire future generations of researchers in this way. In our quest to find and highlight excellence in research over the past 17 years, the Infosys Prize has been awarded to 104 stellar scientists and scholars from India around the world so far. We have hit the century mark this year. Thank you for that clap, even bigger. Okay. Their work holds the potential to impact our lives. In the 20th century, we have been fortunate to have used a scientific insight many scientific insights for time-saving innovations. In some cases, innovation has even life-saving, like penicillin innovation. But these kinds of innovations sometimes is a double-edged sword, my friends. We often face ethical dilemmas while implementing these innovations. For instance only, the energy that powered our past industrial times has led to a climate crisis that demands an immediate transition to renewable energy. We are also battling the digital isolation, where we are more connected yet lonelier than ever. I'm sure you all agree with me on this. Innovation has got us here, but wisdom must lead us forward. That's very important. Our challenge is to ensure that the technology of tomorrow doesn't just make us faster, but better too at caring for everyone, including nature. It's my honor once again to welcome you all to this celebration of scientific excellence. That finishes my formal speech, but the exciting news that you all want to hear, I'm sure you are all eagerly awaiting for that. It is none other than among us, there is a gold medal winner in the cadre of Stephen Hawking, Chandrasekhar, Einstein, Herschel, Charles Babbage. He is in the midst of us here. You all want to know who it is? He just got the news day before yesterday that he has been given a gold medal. It's given by he was honored with the 2026 Royal Astronomical Society Gold Medal Award. It is none other than Professor Srinivas Kulkarni, who is the jury chair for physical sciences. He is among us here. Even bigger hand, please. What a way to celebrate our excellence for 2020 in the midst of an Einstein of 22nd century. Thank you all.
Thank you, Mr. Dinesh. Mr. Dinesh, if you could take your seat on the stage, please. And thank you for that wonderful news about Professor Srinivas Kulkarni. Well, let's begin our prize ceremony with the first award category for this evening, economics. Our laureate is currently a professor at MIT and having received his PhD from Harvard in 2013. A young scholar, his research delves into inadequately understood market design approaches, bringing together intellectual curiosity and social purpose. But to tell you a little more about our winner's work and to announce the award, it is my distinct pleasure to introduce the jury chair, Professor Kaushik Basu, Professor of Economics and the Karl Marx Professor of International Studies at Cornell. He is the former Chief Economist of the World Bank and was the Chief Economic Advisor to the Government of India. He's a Fellow of the Econometric Society and the author of several books. He has published widely in the areas of development economics, industrial organization, game theory, and welfare economics. In May 2008, he was awarded the Padma Bhushan by the Government of India. Please join me in welcoming Professor Kaushik Basu.
The Infosys Prize 2025 in Economics is awarded to Nikhil Agarwal. Professor of Economics at MIT, for his contribution to research on market design. Professor Agarwal has made pioneering contributions, including the development and implementation of path-breaking methodology for empirical studies of allocation mechanisms, including school choice, medical residency, and kidney exchange. How difficult the problem of matching is, to get a sense of that with hundreds and thousands of people looking for something, hundreds and thousands of people trying to sell something. How difficult the matching problem is, to appreciate that, it is worthwhile going back to almost the start of what we describe as modern economics, which is Adam Smith. Adam Smith, puzzled by the order in the world, the fact that people are finding matches, selling whatever they are trying to sell, described the sellers very well. Described the buyers, what are they trying to do? They are seeking their own happiness, utility, etc. Sellers are trying to make profit. He describes both very well. When it comes to matching, how do they find each other? You see Adam Smith doing a bit of a cop-out. He calls it the invisible hand that brings them together, and doesn't quite dissect how that happens. But staggering big work, it sets economics rolling, and within another 40, 50 years, a couple of mathematicians, engineers, with an interest in, after all, demand is a set of equations, supply is a set of equations, they get into this. And roughly 100 years later comes out another staggering big work from Leon Walras, who, a mathematician, who writes up Adam Smith's system fully in equations, describing the buyers and the sellers perfectly. How do they get together, find each other, one another? Once again, there is a bit of a cop-out. He calls it the imaginary auctioneer brings them together. How the imaginary auctioneer manages to bring so many people together is not quite explained. Huge contribution, but it's left open. Over the last 30 years or so, people have got seriously engaged in this problem, because if you need some human organ and there are donors, you need also to be matched. It's not just the total aggregate demand and aggregate supply, you need to find your match. If you're applying to college, you have your preferences, the college has preferences about who they want. How do you find a match? You can get these massive mismatches. This is where there was theoretical contribution, bringing again some certain amount of maths to work out the matching that takes place, and then very big empirical contributions, which is where Nikhil's work primarily comes in, and I do want to talk a little bit about this. One thing that Nikhil in his presentation yesterday pointed out, that just the pure understanding of how this matching takes place does not compel you into any policy position, which is actually David Hume's dictum, that an is analysis does not push you into a should implication. That is left to the policymakers. A little bit formal description, and I'll close. Nikhil Agarwal is the Paul A. Samuelson Professor of Economics at MIT. He is a leading authority on market design who has helped bring this literature into real-world applications by collecting and analyzing large data sets. This is an exceptionally challenging task, as I was trying to explain just now, that requires command over nearly the entire range of economics, from equilibrium analysis with strategic interactions, which is what game theory is, to state-of-the-art econometrics with hard identification problems. A highly skilled microeconomic theorist and applied econometrician, Nikhil Agarwal developed and applied innovative tools to analyze real-world allocation mechanisms, such as school choice, matching over there, medical residency matching, and kidney exchanges. His research connects market design, industrial organization, and econometrics, turning a once theoretical research that improves education, health, and labor market outcomes. His work has transformed this rudimentary literature into one anchored in data, providing new insights into policy making. Nikhil Agarwal did his BA in economics and mathematics from Brandeis University, and in 2013 he got his PhD in economics from Harvard University. A recipient of the Sloan Research Fellowship, Agarwal's research is supported by the NIH and NSF. The jury this year consisted of Levon Barsegian, Lata Gangadharan, Ajit Mishra, Sudipta Sarangi, Tavneet Suri and me. Two of them are here in the audience. As we converged to the name of Professor Nikhil Agarwal for this year's Infosys Prize, we were bowled over, and I'm not exaggerating, by the excellence of his work. Now, taking advantage of his youth, let me drop the professor and just say, Nikhil, what is especially heartening is that you are bringing your skills to bear on matters of great importance for human welfare, which will hopefully be a step towards a better world. Keep up the good work. My warmest congratulations.
Thank you, Professor Basu. And before I call our winner on stage, here is a video of Professor Agarwal talking about why he is drawn to researching economics and its applications. Can we have the video, please?
I am drawn to economic research because it can make a tangible impact on society. In collaboration with practitioners and policymakers, it offers a clear path to making a positive difference. In many areas, such as organ allocation, school choice, and job matching, it would be unethical to use money to allocate resources. Life-saving organs should not go to the highest bidder. These decisions shape education and healthcare, so they matter deeply. A successful transplant can transform a patient's life and their families. Similarly, getting into the right school can have a lasting impact. But because these systems do not work like traditional price-based markets, analyzing these systems using tools that are familiar to economists has been a long-standing challenge. Along with my collaborators, I have developed data-driven methods to analyze these systems to identify what works, what does not work, and how to improve efficiency and fairness. The work in this area has provided new insights that has enabled better policy design. Looking ahead, I want to apply this approach much more broadly, using economics and data to build better systems and demonstrate its value across a diverse set of applications.
Please join me in welcoming on stage Professor Nikhil Agarwal. May I request Mr. Mohandas Pai, trustee for this award category, and Professor Basu to join us for the presentation. And now I request Professor Randy Schekman to present the Infosys Prize in Economics to Professor Nikhil Agarwal. Thank you, Mr. Pai. Thank you, Professor Basu. Thank you, Professor Schekman. Professor Agarwal, a few words, please.
Thank you to the Infosys Foundation and the jury for this truly humbling honor. Many of the previous winners of this prize are role models who I can only aspire to emulate. The work on empirical market design recognized in this award would not be possible without many of my collaborators and students. I'd especially like to acknowledge Paolo Someni, who's been a partner in crime from the very beginning in the very early days. Parag Pathak, who has mentored me and collaborated with me and gave me my start in this field. And then Ita Ashlagi, who initiated the program on kidney exchange design very early on. I'm also deeply grateful to many of my teachers who have inspired me. Sanjeet Basu and Linda Bui before graduate school, and Al Roth, Susan Athey, and Ariel Pecos, whose perspectives and ideas continue to guide my research to this day. Most importantly, I would not be standing here without the support of my loving friends and family, many of whom are here today. My dearest wife, Ellie, is a pillar and a moral North Star in our family. And my parents, who have always fed my sister and my curiosity and nurtured a value system in which the pursuit of knowledge is prized. Thank you, everyone.
Congratulations and thank you, Professor. Well, we all know about matchmaking internet apps. They only promise perfect results, but Professor Agarwal's algorithms actually deliver things that matter. Kidneys to patients, students to schools, no swipes required. Well, our next laureate this evening, and this is in the field of engineering and computer science, is a professor at the University of Toronto. His research is chasing the underlying algorithms that process increasingly complex data sets and interconnections. The jury chair for this category is the president of Oregon State University, Professor Jayati Murthy. She's a leader in higher education teaching, research, and science. She's the author of over 330 technical publications, and her research interests include nanoscale heat transfer, computational fluid dynamics, and submicron thermal transport. She is an alumnus of IIT Kanpur and a member of the National Academy of Engineering, a foreign fellow of the Indian National Academy of Engineering, a fellow of the American Society of Mechanical Engineers. She won the ASME Heat Transfer Memorial Award in 2016 and the ASME Kate Gleason Award in 2023. Please join me in welcoming Professor Jayati Murthy.
The Infosys Prize 2025 in Engineering and Computer Science is awarded to Sushant Sachdeva, Associate Professor of Mathematical and Computational Sciences at the University of Toronto, for his deep insights into mathematical optimization and the resolution of long-standing open questions in algorithmic theory. His work has established new standards on achievable performance in computational problems affecting information flows across societal lifelines, including the internet, transportation, and communication networks. Now, it's my great pleasure to introduce you to some of the details of Professor Sushant Sachdeva's work. Now, as I said, Professor Sachdeva is an associate professor of mathematical and computer sciences at the University of Toronto, but he is also on the faculty of the Vector Institute, and he is also simultaneously working at OpenAI, which you all know. Now, he holds a BTech degree in computer science and engineering from IIT Bombay and a PhD in computer science from Princeton University. He did his postdoctoral work at Yale University. Now, Professor Sushant Sachdeva's research focuses on foundational mathematical models that undergird computational frameworks that power modern life. Now, these methods are vital to the conceptualization and design of, for example, transportation networks, telecommunication, and electrical grids. Fundamental to these computing frameworks are algorithms that process vast amounts of data and which address complex networks and interconnections. Furthermore, as data sets and networks become larger and more complex, the underlying algorithms must scale efficiently while maintaining accuracy. Many of these problems are not new. Computer scientists and mathematicians have worked on them for decades, but the scale and complexity certainly are. It's fair to say that despite concerted effort, true breakthroughs are rare. Now, Professor Sachdeva's work marks such a breakthrough. So let me try and give you a layman's flavor of one of his most important contributions, an almost linear time algorithm for maximum flow. Now, what is maximum flow? Well, consider a transportation network, a network of roads, for example. We would like to know the maximum number of vehicles we can transport through that network at once if various legs of the road network have capacity limits. So, for example, some are 4-lane highways, some are 2-lane, some are dirt roads, etc. A more general version of the problem also seeks to minimize cost. Now, this is an old problem in computer science, and it has been studied since the 1950s. and many have offered solutions over the decades. Now, for example, the solution by Ford and Fulkerson offers a multi-step solution scaling as m squared, where m is the number of links in the network. Now, other approaches have lower exponents. For example, m equal to 1.5 or m equal to 1.33. But Professor Sachdeva and his team were able to devise an algorithm that scales nearly linearly. That is, as you look at bigger and bigger networks, the algorithm's computational time scales as some multiple of m. So if you double the size of the network, the computational time approximately doubles. It does not increase 10 times or 1,000 times or even worse, and that is really important. This algorithm has been described by colleagues as a slam dunk or as absurdly fast. You can see how such an algorithm could find wide use in transportation networks, in telecommunication networks, in internet data flows, airline scheduling, and so much more. Professor Sachdeva bridges mathematical analysis, optimization, and computational problem solving to create unified frameworks for flow problems such as bipartite matching, minimum cost flow, optimal transport, and matrix scaling. He smoothly integrates linear systems, linear programming, and network flow techniques. And to achieve this, Professor Sachdeva leverages innovations in graph approximations and sparsification techniques. In addition to his breakthroughs in the maximum flow algorithms, Professor Sachdeva has made significant contributions to graph sparsification, efficient preconditioners, and optimization methods for regression tasks, among others. Now, in machine learning, his work improves the convergence of autoencoders. He has also done highly impactful work by developing noisy quadratic models, which are theoretical proxies for large neural network training. His work thus pushes the boundaries of scalable, intelligent computation. No surprise then that Professor Sachdeva has received numerous awards and fellowships, starting with an early recognition signaling high promise, the IIT Bombay President of India Gold Medal, and more recently, the Google Faculty Research Award. His contributions in the field have been recognized with the Sloan Research Fellowship and the Foundations of Computer Science Best Paper Award. Our engineering and computer science jury looked at a large number of highly qualified nominees and concluded that no one was more deserving of the Infosys 2025 Prize in Engineering Computer Science than Professor Sushant Sachdeva. And so on behalf of the jury, congratulations, Sushant.
Thank you, Professor Murthy. And here's a video of Professor Sachdeva on his quest for breakthroughs in stalled research. Can we have the video, please?
I design algorithms to solve optimization problems efficiently. One of my major contributions is an algorithm for efficiently solving the maximum flow problem, a problem first posed around World War II that asks how quickly can we move resources from one point to another. This simple question became central to algorithms and computer science, modeling transportation, communication, and networks. After decades of stalled progress, we achieved a breakthrough in 2022, achieving algorithms that run almost linearly in the graph size. So if a graph grew tenfold, runtime would also only grow tenfold, something once thought impossible. Our approach also handles dynamic graphs, making it vital for real-world systems like traffic routing and data flow. Today, we are at the cusp of a revolution where we expect that models will discover new knowledge. My goal is to accelerate this discovery by combining algorithms and AI, pushing computational boundaries and opening new research frontiers.
Please join me in welcoming on stage Professor Sushant Sachdeva. And may I request Mr. S.D. Shubhalal, the trustee for this category, and Professor Murthy to join us for the prize presentation. And may I request Professor Randy Schekman to present the Infosys Prize in Engineering and Computer Science to Professor Sushant Sachdeva. Let's give him a big hand, ladies and gentlemen. Thank you. Thank you, Mr. Shibalal. Thank you, Professor Murthy. Thank you, Professor Schekman. And Professor Sachdeva, a few words, please.
Thank you. My deepest gratitude to the jury and the Infosys Science Foundation for this recognition that's really beyond my wildest dreams. I'd like to thank some of my mentors who've really influenced my path here and got me excited about this field. Professor Sundar Vishwanathan, Sanjeev Arora, Daniel Spielman, and Nishit Vishnoi, without whom I would not have gotten the initiation I needed into the field here. I'd like to thank our powerhouse of a team, my collaborators, Rasmus King, Richard Peng, Yang Liu, Li Chen, and Max Probst Gudenberg, who we worked for years together on the problem that led us here. But eventually, I'd like to dedicate this award to my biggest supporters, my wife Pushkarni, who's soldiering every day to help support all of us, my mother and late father, who've really gone to great lengths to help me realize my potential, and my uncle, my Chachaji, who ignited the fire of curiosity that led us here. Thank you all.
Thank you and congratulations, Professor. If your algorithms are really absurdly fast and slice through complex flow problems at that speed, I think we'll all need new thumbs as our social media feeds start to refresh faster and faster. Well, if you're wondering what our winners are receiving on stage, the Infosys Prize consists of a 22-carat gold medal weighing 55 grams, a citation, and a purse of $100,000 US in each category. The winners are selected by juries consisting of eminent researchers from around the world and who are represented here by our jury chairs. And each jury evaluates the achievements of our nominees against international standards of research, placing the winners on par with the finest researchers in the world. So, congratulations. Well, in the next category, and this is for humanities and social sciences, our laureate this year is Associate Professor at the University of Chicago. He's a PhD from Columbia and a member of the Harvard Society of Fellows, and was trained in classical Greek and Latin before he turned his attention to Sanskrit and other South Asian languages. And to tell you more, I'm very pleased to introduce to you the jury chair for humanities, Professor Akhil Bilgrami, the Sidney Morgan Besser Professor of Philosophy and the Professor for the Committee of Global Thought at Columbia. He's the author of several books and is currently writing a book on Gandhi's philosophy, as well as a longer work on the nature of practical reason. He's been the chair of the Philosophy Department at Columbia, the director of the Heyman Center for the Humanities, and the director of the South Asian Institute. He held the Radhakrishnan Chair in India and has been the recipient of fellowships and grants from the Mellon Foundation, the Ford Foundation, the National Endowment of the Humanities, as well as the Lush Foundation. Please welcome the very distinguished Professor Akhil Bilgrami.
The Infosys Prize in the Humanities and Social Sciences is awarded to Andrew Oddett of the University of Chicago for his outstanding work as a philologist, linguist, and intellectual historian of India. The jury that chose him consisted of Veena Das, Kalpana Kanarivan, Prachi Deshpande, Nirja Jayal, David Schulman, and myself. His major work, Language of the Snakes, establishes Andrew as the most prominent living scholar of Prakrit. It is a work which repudiates certain standard ways of understanding Prakrit, especially the relations that it bears to the overwhelming centrality of Sanskrit, rescuing it from a perceived peripheral status, demonstrating the ways in which it was a forerunner of the great Kavya tradition in Sanskrit literature, and subtly elaborating the ways in which it stands side by side with Sanskrit in a symbiotic relation throughout the entirety of a millennium. One can characterize the nature of human language as serving at least three large functions. One, and the most obvious, is that language is the most sophisticated and structured form of communication in the lives of the most sophisticated cognitive and conative creatures that we know of. Another is that language allows us to get a distance from the many habits and dispositions that we are immersed in, hold one or other of them at a distance as something to critically think about and ask reflective questions about it. In short, language gives us the possibility for self-consciously critical reasoning about our hitherto unself-conscious activity. And a third function is that language is the repository of a tradition and the wisdom of a tradition that has accumulated through the exercise of such reason of this reflective kind within the practices of a tradition. For me as a philosopher, one of the most interesting things I've learned from reading Ollitt's book is that it would be too general and too omnibus a thing to say that Prakrit was a repository of a tradition. We don't get the special character of Prakrit as a language until we see that the tradition that it primarily and pervasively carries as a language is a literary tradition. Thus, even the formal aspects of Prakrit, not to mention its elaborate role in expressing the assertions and the scope of power as it was exercised in the Satavahana kingdom of Western India and the Deccan, according to Ollitt, are thoroughly inflected and to some extent even constituted by its literary forms and features. What this means is that when it comes to Prakrit, grammar and philology, two seemingly different disciplinary pursuits, are too integrated to be seen as separate forms of knowledge in the way that might well be true of other languages. Let me conclude by saying something about Ollitt's current major work, which is soon to be published. It is on a topic that is at the heart of contemporary debates in theoretical linguistics and philosophy of language in the West, the nature of sentence meaning. I'm going to try to convey the issue at stake here to you by situating it in a wider question about the nature of human action. The philosopher Ludwig Wittgenstein once raised a question about some actions being more basic than other actions. He gives the following example, which I adapt slightly for my purposes. Suppose I wave to a friend. Philosophers, Wittgenstein says, are prone to say that the action of my waving to a friend breaks down into a more basic action, which is the action of my moving my arm. So I wave to a friend by performing an action which is conceptually more basic, the action of moving my arm. So one might say that a basic action is something you do, and there's nothing else you do in virtue of which you do it. Now take the sentence, the train is about to leave. Suppose I convey to you that you should hurry up by uttering that sentence. The train is about to leave. I utter it with a view to conveying to you that you should hurry up. But the meaning of the sentence, the train is about to leave, is not hurry up. The meaning of the sentence has to do with vehicles of transportation, departure times, and so on. And so the question arises then, what is the relationship between that meaning and my conveying to you that you should step up your pace? What is the conceptual mechanism that underlies the talk of by when I say I conveyed hurry up by saying the train is about to leave? Ollett's recent work is a masterly elaboration of how Indian philosophers expended an enormous amount of ingenuity in spelling out the details of that mechanism, registering a variety of disagreements on detail and providing, on the way, rigorous analyses of such technical linguistic notions as compositionality, holism, atomism, inference, entailment, implicature, and Ollett himself concludes this learned account by once again expressing his own instinct for the centrality of literature to language by putting on center stage an idea that he distinguishes from all these other notions and which he calls literary suggestion. And in the insightful detail by which he does so, I believe, he surpasses in interpretive innovations the ideas of his own mentor, Sheldon Pollock, on the question of how to understand the way in which literature can affect the formal questions that arise in the study of language. That's quite an achievement. Congratulations, Andrew.
Thank you, Professor, and that was certainly food for thought on philosophy. Well, before I call our winner on stage, here's a video of Professor Andrew Ollett reflecting on languages, on words, and cultures. Can we have the video, please?
I've always been interested in ancient languages. I taught myself Latin, and then studied Greek, and then Sanskrit. Very early in my study of Sanskrit, I realized that it came from a culture that took language and philology extraordinarily seriously. There was a civilizational project of attention to words. Then came the question that shaped my research. Why does Prakrit exist alongside Sanskrit as a literary language? What is its role? My research investigates this language order in pre-modern India. Why do cultures value and organize languages the way that they do? Which languages matter? Which languages can you compose literature and philosophy in? Studying ancient languages is not about utility. It's about having a conversation across time with some of the smartest people who ever lived. It enriches our understanding of the world and deepens the intellectual conversations we need as human beings.
Please join me in welcoming on stage Professor Andrew Ollett. And may I request Mr. Nandan Nilekani, the anchor trustee for this category, and Professor Bilgrami to join us for the presentation. And I request Professor Schekman to present the Infosys Prize in Humanities to Professor Andrew Ollett. Let's give them a big hand. Thank you. Thank you, Mr. Nilekani. Thank you, Professor Bilgrami. Thank you, Professor Schekman. Professor Ollett, I invite you to say a few words.
Got it. So, first of all, I'd like to thank everyone without whom I would not be here. If you're hearing this, you know who you are. For those of us who work on the non-modern, non-West, recognition of our research is rare, even at our own institutions. So for that reason, I'm extremely grateful. I'm extremely grateful to the Infosys Science Foundation and the jury. Nanu tumba kritagyan agadene. Thank you.
Congratulations and thank you, Professor. Thank you for keeping our old languages alive. As Charles Darwin said, a language, like a species, when extinct, never reappears. Well, our next laureate in the category of life sciences is researching how our little cells keep the stuff of life, our DNA, from going extinct. She's an associate professor of our very own National Center for Biological Sciences in Bangalore. And she received a PhD in 2011 from Oxford and subsequently did her postdoctoral research at MIT. To announce the Infosys Prize in Life Sciences, I am pleased to introduce the jury chair, Professor Mruganka Sur. Dr. Sur is the Newton Professor of Neuroscience, the director of the Simon Center for the Social Brain, and an investigator at the Pickover Institute for Learning and Memory at MIT. He's a pioneer in studying the organization, plasticity, and dynamics of the brain's cerebral cortex using experimental and theoretical approaches. He received the Distinguished Alumnus Award at IIT Kanpur and is an elected fellow of the Royal Society in the UK, the US National Academy of Medicine, the American Academy of Arts and Sciences, the World Academy of Sciences, and the Indian National Science Academy. Please welcome Professor Mruganka Sur.
The Infosys Prize 2025 in Life Sciences is awarded to Anjana Badrinarayanan. Associate Professor at the National Center for Biological Sciences, Bangalore, for pioneering contributions to understanding mechanisms of genome maintenance and repair. Through innovative live cell imaging combined with genetic and cell biological approaches, her work has revealed fundamental principles of how DNA damage is repaired, demonstrated mutagenesis in non-dividing cells, and identified novel pathways of mitochondrial DNA damage responses, thereby illuminating principles central to life and evolution. The jury for the Life Sciences Prize, including Paola Arlotta, Tejal Desai, Shankar Ghosh, Satyajit Mayer, Imran Siddiqui, and myself, unanimously selected Anjana Badrinarayanan for the prize. Our decision was based on her fundamental, deep basic science discoveries that also have tremendous importance for understanding and treating diseases. Anjana received her PhD from Oxford University and did a postdoc at MIT before joining NCBS. Her work for a long time, and we were impressed by her committed dedication to understanding how genomes are maintained, how they are repaired, how they replicate, and even reorganize. Every cell in our body, 30 trillion of them, carries all of our genome or genetic information in the form of DNA. Our genome has 3 billion with a B chemical pairs and about 1 meter long when you uncoil it, but it's coiled up tightly and folded into cells that are about 1/10 the width of a human hair. That's an astonishing feat of nature. Our DNA at the same time is being damaged all the time. Amazingly, an average cell in our body undergoes 10,000 and perhaps up to 1 million damaging events daily from internal sources such as byproducts of metabolism, including reactive oxygen species, and external sources such as radiation, ultraviolet light, or chemical insults. Every time we go out into the sun, for example, our skin is bombarded with ultraviolet rays that break up our DNA. This is why we have skin irritation or rash or pain or inflammation, as the skin tries to deal with damaged cells and shed them and make new skin cells. In fact, stem cells in the skin make new cells all the time to replace dead or damaged cells, or to repair a cut when we cut our skin. And every time new cells are made, not only in the skin, but also new muscle cells, for example, when we exercise, or new blood cells in our bone marrow to continuously replenish our blood supply. New DNA is synthesized. Every cell in our body has the entire genome. Most of the genes are suppressed. Only the genes that make new skin cells or blood or muscle are turned on. And it is crucial that every cell has an error-free copy of this DNA. And of course, during development, when we or our children are made in utero and then outside, we have one fertilized cell that divides into two, then into four, and on and on and on, till we have the trillions of cells that comprise our body and brain. This entire process of duplicating DNA with every cell division is actually remarkably prone to errors and damage. And in fact, uncorrected errors during cell replication are responsible for devastating developmental disorders, including a brain disorder that my lab has studied for several years called Rett syndrome. So it is critical that such damage in both adult cells and developing cells be accurately repaired. And this is Anjana's contribution. How do you repair damage to DNA? Anjana's work remarkably shows how a particularly severe kind of damage called a double-stranded break, where both strands of DNA coil together, both strands get severed. It's a brutal kind of damage, and it needs to be repaired. Using a simple model system, all progress in life sciences relies on appropriate model systems. You can hardly study human beings directly except look at them. But you need cellular models to study fundamental processes of life. And Anjana early on identified a simple, humble bacterium in which you could induce such double-stranded breaks, and in which the DNA is not compacted into the nucleus, but is spread through the cell, called the cytoplasm. And she showed that after such a break, cells have proteins that act like motors that search the entire genome to find the right partner with which to repair the break. It's an astonishing fact of life. Her work is fundamental science, using clever tools that she developed and clever cell biology and very clever genetics. But it is of the highest practical importance because it applies to all organisms, including human beings. And her findings paved the way for understanding many processes that involve DNA damage, such as cancer or aging, and for developing strategies to counter them. Anjana's discoveries demonstrating mutagenesis, mutations in genes, in non-dividing or non-replicating cells, in so-called mature cells, has overturned classical paradigms that link mutations solely to replicating cells. In fact, one of the most exciting aspects of her work is the demonstration that we have known in many other systems as well, that the genome that we think specifies that the genome is destiny, yet the genome is plastic. It is changing all the time. And this provides mechanistic insight into how dormant bacterial populations evolve and acquire antibiotic resistance, which is a major problem in India and many other countries. Her studies have revealed how mitochondrial DNA, a key component of cells, which is essential for producing energy, which is central to life, is repaired and cleared following damage. Anjana has built an outstanding research group at NCBS that has enabled these discoveries. Through her creativity, her technical innovation, and conceptual rigor, Anjana has provided deep insights into how genomic integrity is maintained across domains of life. She has established herself as a leader in the molecular biology of DNA replication, recombination, and repair. These are fundamental processes of life, and they are the key to understanding some of our deepest diseases and how to treat them. So congratulations, Anjana. We are delighted to award you the 2025 Infosys Prize in Life Sciences, and we look forward eagerly to many more discoveries in the future.
Thank you, Professor Sur. And here's a video of Professor Anjana Badrinarayanan talking about how her curiosity led to uncovering the mysteries of our cells. Can we have the video, please?
I've always been curious, not just about why life works, but how. DNA, the blueprint of life, faces thousands of damages every day, yet repair is fast and accurate. How does this happen? A question we've been exploring in the lab is about homology search, how a broken piece of DNA finds an exact match inside the cell. We've developed live cell imaging-based technologies to probe this process inside living cells. Using this, we've uncovered molecular motors that power search. We've solved a mystery that has remained unsolved for decades. Our work has also showed that dormant cells can mutate, reshaping our ideas of how antibiotic resistance can emerge. We've also revealed how mitochondria clear DNA damage to keep cells resilient. Genomes are not rigid, they are plastic, capable of change. Understanding this plasticity has profound implications for evolution, aging, disease, and the emergence of antibiotic resistance. Now we are asking, what is the journey DNA takes as it goes from one organism to another? How does something foreign become part of you? That is where we are going next.
Please join me in welcoming on stage Professor Anjana Badrinarayanan. May I request Mr. S.D. Shibulal to join us on the stage, and may I request Professor Sur to join the presentation. And I request Professor Schekman to present the Infosys Prize in Life Sciences to Professor Anjana Badrinarayanan. Thank you, Professor Schekman. Thank you, Mr. Shibulal. Thank you, Professor Sur. Professor Anjana, a few words, please.
Thank you to the Infosys Science Foundation, the jury, and the trustees for this incredible honor. It is special to stand among stellar scientists, several of whom I look up to for inspiration myself. Science is never a product of an individual. It needs institutes that protect and nurture freedom and curiosity, and I'm incredibly grateful to call NCBS my home for that. It needs mentors who shape how we see the world and collaborators who enrich the work. My gratitude to all of them, especially David Sherritt and Michael Laub. It needs family. I am grateful to my parents for creating a home that celebrates intellectual pursuits, and my husband who shared the uncertainty, the long hours, and the quiet doubts. And most importantly, it needs people. This award belongs as much to my lab members, students and postdocs who bring imagination, rigor, and courage to science every day. Working with them is the greatest privilege of my job. Thank you again for this recognition. It leaves me feeling encouraged and motivated to keep reaching harder and harder for questions ahead. Thank you.
Congratulations. You know, they say that instruction manuals are like diets. Everyone ignores them until the disaster strikes. But it appears our cells are a step ahead in preserving our DNA instructions. And speaking of manuals, our next category is mathematics, which seeks to provide the ultimate instruction manual for the universe. And our laureate in this category is an associate professor in the School of Mathematics at the Tata Institute of Fundamental Research in Mumbai. His research lies at the intersection of conformal dynamics, complex analysis, and Teichmuller theory. I don't know about you, but I have no idea what all that means. So to explain it better, I'm very happy to introduce you to the jury chair for mathematics, Professor Chandrasekhar Khare. Professor Khare is from the University of California in Los Angeles. He's a number theorist, and his work with Jean-Pierre Wittenberger proved Serre's celebrated modulatory conjecture. He's received a number of honors and awards, including the Fermat Prize in 2007, the Cole Prize in 2011, and our very own Infosys Prize in 2010. In 2012, Professor Khare was elected as a Fellow of the Royal Society. His recent book, Chasing a Conjecture Inside the Mind of a Mathematician, describes the mysterious ways by which ideas arise in the mind and take flight. Please welcome Professor Chandrasekhar Khare.
Professor Sabyasachi Mukherjee of the Tata Institute of Fundamental Research is the winner of the 2025 Infosys Prize for the Mathematical Sciences. He is awarded the Infosys Prize for his powerful and surprising work connecting to apparently completely different topics. The dynamics of actions of Kleinian groups on one hand, and those arising from iterations of holomorphic or anti-holomorphic maps in complex dynamics. Mukherjee's results have reshaped our understanding of the subject. So the math jury consisted of Ritabrata Munshi from ISI Kolkata, Kavita Ramanan from Brown University, Ellen Eno from Berlin, and Andrew Wiles from University of Oxford. We have Ritabrata and Kavita in our midst. So let me try and explain in very broad strokes what Dr. Mukherjee's prize-winning work is about and the field of mathematics in which it is situated. So dynamical systems are mathematical models for systems that evolve over time. They cover systems ranging from the planetary system with the sun at the center and planets moving around it, to the weather systems around the world that are very complex and notoriously hard to predict. Mathematicians study the stability of such systems and their long-term behavior. This matters. The stability of the planetary system, for instance, clearly has consequences for our existence on Earth. One of the founders of this subject was the great French mathematician Henri Poincaré, working around the turn of the 20th century, so roughly 100 years ago, 125 years ago. He studied, amongst many things, the stability of the planetary system, the famous and famously unsolvable three-body problem involving the Earth, Moon, and Sun interacting through gravity arises naturally in this context. So Dr. Mukherjee studies dynamical systems of several kinds. What is remarkable about his work is that he has uncovered deep and unexpected connections between systems that appear at first sight to have nothing to do with one another. Poincaré once described mathematics, so this is as good a definition you can have of math as any. So he defined mathematics as the art of giving the same name to different things. One of the astonishing aspects of Sabya's work is precisely this. He gives the same name to very different dynamical systems, in essence. His results establish new and striking instances of what is known as the Sullivan Dictionary, developed in the 1980s through Dennis Sullivan's pioneering work. This dictionary reveals deep parallels between dynamics arising from Kleinian groups and those arising from the iteration of rational maps. So now, like in poetry, a metaphor in mathematics, so in some ways Sabyasachi's work is about sort of developing such a metaphor. A metaphor in mathematics gains its power by relating things that seem very different through terms of comparison that are hidden, surprising, and subtle. So in Sabyasachi's work, relating such disparate dynamical systems requires the construction of intermediaries that can mediate between them. For this purpose, he introduces and develops ideas known as matings and correspondences, structures that act as bridges between different dynamical worlds. The construction of matings is both an art and a science. Art, because it requires deep intuition to discover them, and science, because it requires rigorous proof to show that they truly work. Through these ideas, Sabyasachi's work reveals unexpected similarities between the parameter spaces of very different dynamical systems. Now here I'm going to launch a defense of mathematics. While mathematics is widely acknowledged as useful, often described as the language of the universe, it is sometimes accused, unfairly at least to my mind, of being dry, technical, or even soulless. So Sabyasachi's work neatly refutes this charge, not only through the beauty of its ideas, but also through the beauty of the pictures that emerge from it. So if you look at the prize brochure, you can see lots of lovely pictures emerging from Sabya's work. One of the parameter spaces studied in his work is known as the tricon, a shape reminiscent of the three-cornered hat popular in 19th century Europe. That hat was later replaced by the bicon in Napoleonic times. But mathematics, unlike fashion, is not fickle. And the tricon remains very much in mathematical vogue and is one of the key players in Sabya's work. I would like to end by saying most of Sabya's work has been carried out while he has been based in India at the Tata Institute of Fundamental Research in Mumbai. Together with his colleagues there, he is helping to build a vibrant and exciting group of young researchers in dynamical systems. Congratulations, Sabya, on your brilliant and beautiful work.
Thank you, Professor Kare. And here is a video with Professor Sabyasachi Mukherjee talking about building bridges to better understand chaotic dynamical systems.
I work on dynamical systems. The area of dynamical systems started about 125 years ago with the question whether the planetary system is stable or whether things will crash eventually. Today, dynamical systems find applications in many areas of science: statistical physics, biology, computer science, and many more. For a century, we have seen many parallels among them, and my work focuses on building bridges and connections that can eventually transform the way we understand chaotic dynamics. Mathematics thrives on a holistic approach. A problem can come from any area of science, and we should not dismiss it as an applied problem, because the tools that we develop in order to solve an application-oriented problem can lead to beautiful areas of pure mathematics. I want to push this new area of mathematics further, turning it into a full-fledged theory. My goal is to uncover deeper relationships and build bridges across systems and find connections that can transform the way we understand chaotic dynamics.
Please join me in welcoming on stage Professor Sabyasachi Mukherjee. And may I request Mr. K. Dinesh, the anchor trustee for this category, and Professor Kare to join us for the presentation. And I request Professor Randy Schekman to present the Infosys Prize in Mathematics to Professor Sabyasachi Mukherjee. Let's give him a big hand, please. Thank you, Mr. Dinesh. Thank you, Professor Curry. Thank you, Professor Schekman. Professor Mukherjee, say a few words, please.
This is truly a wonderful honor, especially to be placed in the same bracket as some of the extraordinary researchers and mathematicians who have received this award in the past. I'm grateful to the trustees, the jury members, and the entire Infosys Science Foundation for considering me worthy of this award and for putting this amazing event together. I'm grateful to my parents for allowing me to flourish in my own way, and to my brother and my family for all the support over the years. A special word of thanks to my wife for letting me stay lost in my abstract world. I would like to mention Mahan MJ and Misha Lubitsch, who have been the strongest pillars in my mathematical career. They have taught me how to think about mathematics, which is more important than just doing mathematics. Finally, I would like to view this as a responsibility to make small yet meaningful contributions to the mathematical research in India. Thank you.
Thank you and congratulations, Professor Mukherjee. As G.H. Hardy said, a mathematician, like a painter or a poet, is a maker of patterns. There is art in math, after all. This year's winner in physical sciences is a professor of chemical engineering and chemistry at Caltech. He's a graduate of Stanford and UC Berkeley and trained as a postdoctoral fellow with Nobel laureate Robert Grubbs. To announce the prize, it is my pleasure to introduce the jury chair, Professor Srinivas Kulkarni, George Ellery Hale Professor of Astronomy and Planetary Science at Caltech, and the former director of the Caltech Optical Observatories. His primary interests are in the study of cosmic explosions of neutron stars and developing new methodologies for astronomical research. He's a winner of several accolades. In 2024, he was awarded the Shaw Prize in Astronomy. And as Mr. Dinesh said earlier today, he is the winner of the most prestigious 2026 gold medal of the Royal Astronomical Society, joining an awardee roster that has names like Babbage, Einstein, Hawking, and Chandrasekhar. He was also, just yesterday, selected as the Messenger Lecturer at Cornell, previously given to eminent researchers like Feynman, Oppenheimer, Pauling, and Eddington. Ladies and gentlemen, please put your hands together in congratulations and to welcome Professor Srinivas Kulkarni.
The Infosys Prize 2025 in Physical Sciences is awarded to Karthik Mantiram. Let me read the citation. For his pioneering sustainable electrochemical routes to essential chemicals, his breakthroughs in lithium-mediated ammonia synthesis and oxygen atom transfer catalysis have transformed our understanding of electrified chemical manufacturing, demonstrating how renewable electricity can drive selective, efficient synthesis of chemicals that are fundamental to agriculture and industry. Okay, let me explain some of what that actually means. So the ambit of physical sciences is actually quite large. It includes physics, chemistry, astronomy, geology, paleontology, atmospheric sciences, and space sciences. Alchemy is an ancient philosophical and proto-scientific tradition practiced practically across the world, focused on transforming base metals into gold, finding universal cure, and achieving spiritual perfection. Alchemy served as a precursor to modern chemistry, which is the area that is being recognized by the physical sciences panel, of which I'm the chair. My fellow jurors are Yamuna Krishnan, Department of Chemistry, University of Chicago, Spenta Wadia, Professor of Theoretical Physics, ICTS, right here in this town, and Spenta is in the audience here. Peter Zoller, Professor of Theoretical Physics, Innsbruck, Austria. Stephen Kywelson, Professor of Physics, Stanford University. Our winner, in some fashion, is a modern-day alchemist. He wants to use air and water to make critical materials like ammonia, which forms the basis for fertilizers, and epoxides, which is at the root for plastic, foams, fibers, and surfactants. And he wants to do that without any harmful waste products like carbon dioxide or calcium chloride. He and his students have demonstrated the processes in the laboratory. It is not a given that a laboratory process can be scaled up to large scale, that is to industrial scales. Chemical engineering is a subject by itself. In fact, our winner is both a professor of chemistry and a professor of chemical engineering. The rapid progress that is now being achieved in Mantiram's laboratory suggests that large-scale scaling up is possible on a timescale of only 5 years. With this overview, let me explain more concretely the work done by Kartish Mantiram and his group. The human population of Earth now stands at 8.3 billion. Adequate food production for this large number of human beings requires very productive farming. Perhaps the most critical input for productive farming is fertilizers, specifically the need of artificial fertilizers. The urgent need for artificial fertilizers was in fact recognized at the turn of the last century. Chemist Fritz Haber and chemical engineer Carl Bosch invented the Haber-Bosch process to make ammonia, which, as I said, is the key input for artificial fertilizers. The pair were awarded a Nobel Prize. Now, recall that ammonia is NH3, so 1 atom of nitrogen, 3 atoms of hydrogen. Haber and Bosch used molecular nitrogen from air and used the process of steam reforming to extract hydrogen from water. The two gases in appropriate proportions were passed over an ion catalyst. The synthesis, that is to combine 1 atom of nitrogen and 3 atoms of hydrogen to make ammonia, required high temperature, about 400 to 500 centigrade, and high pressure, hundreds of atmospheres. In order to confine this sort of a pressure, you need very large, very rigid structures, so it now becomes a massive undertaking. Not only that, but the process was energy intensive, is energy intensive. It is estimated that synthesizing ammonia through this process, which happens today even, consumes 2% of the global energy budget. Furthermore, it produces this stupendous amount of energy, produces proportional amount of carbon dioxide. Kartish Mantiram took a very different approach. The use of an electrified catalyst. Molecular nitrogen binds to a mesh of lithium, which serves as a catalyst. A proton, that is ionized hydrogen, obtained from water, then interacts with this lithium mesh, upon which both NH3, ammonia, and lithium plus, or lithium ion, are ejected. Lithium ion is recycled and used in the next cycle. This process has no harmful products. It uses electricity generated from, for instance, solar panels. The process is flexible. The group found a combination of sodium and titanium can serve as catalyst just as well, and perhaps even better. So this allows whichever combination of rare metals we want to use to be substituted at the time of actually manufacturing. Most importantly, this process takes place at room temperature and requires very modest pressures, less than 10 atmospheres. The room temperature operation and modest pressure do not place heavy mechanical demands, such as for the Haber-Bosch process. The small scale of operation and the ready availability of solar panels means that the production plants can be distributed across the nation, in particular located close to farming regions, rather than the current approach of having a large centralized facility. This results to low transportation costs. I now come to epoxides, which I mentioned earlier is the primary input for plastics, foam, artificial fibers, and for surfactants. Epoxide, for instance, can be obtained by oxidizing ethylene or propylene, which are hydrocarbons that we get as a part of our petroleum industry. So you'd say, okay, what does it take to directly oxidize these hydrocarbons? The direct oxidation process produces carbon dioxide as a byproduct. Using chlorine, which is a method that was pressed into service some time ago, produces calcium chloride, which is extremely harmful for the environment. Using hydrogen peroxide seems pretty good, except it results in explosions now and then, and so involves fatalities. Montiram and his students have made great strides using a combination of electrolysis and catalyst in synthesizing epoxides. In their technique, the inputs are ethylene or propylene and water. Epoxide is synthesized at the anode, and the hydrogen is produced at the cathode. Note the byproduct of this process is hydrogen, a most valuable product in itself. So far, I have focused on the possible great advances that are likely to result from the work carried out by Montiram. I end this presentation by summarizing the key reasons that led us to selecting Montiram. The artificial synthesis of ammonia has been studied by chemistry for over a century. As you can see, it's an extremely important input for our living, our food source. Kartish exhibited, in our opinion, great creativity in finding a solution through electrical processes rather than thermal mechanical processes. Such a leap requires tremendous intuitive understanding of chemistry. Working in the fertile grounds of Caltech, Karthik identified pathways for engineering implementation, which itself is an achievement. He has thus made a mark both in fundamental chemistry and chemical engineering. We're actually shortchanging him by giving him only one prize. Congratulations, Dr. Montiram.
Thank you, Professor Kulkarni. And here is Professor Kartish Montiram on the persistence and the patience required in research. Can we have the video, please?
Almost 15 years ago, I read a paper about using electricity to convert air and water into useful materials. I couldn't stop thinking about it. I knew I had to start working on this problem. I decided to work on something my group knew nothing about. We started a research group focused on converting air and water into useful chemicals using electricity. For 3 years, we had nothing to show for it. No external grants or papers in those risky new areas. But with perseverance and patience, we got it to work. We developed lithium-mediated ammonia synthesis and a process to make epoxides using water without hazardous reagents or byproducts. Our goal is to replace the petroleum-based supply chain with air, water, and electricity, cutting carbon footprints, mitigating global warming, and improving lives. The promise is that smaller local installations can leapfrog existing massive centralized infrastructure. Our vision is that what happened with electricity production, with wind and solar becoming competitive with conventional power plants, can also happen with chemicals, modular, local, and powered by renewables, rather than large, centralized, and powered by fossil fuels.
Please join me in welcoming on stage Professor Kartish Montiram. And may I request Mr. Chris Gopalakrishnan to join Professor Kulkarni for the presentation. And I request Professor Schekman to present the Infosys Prize 2025 in Physical Sciences to Professor Kartish Montiram. Let's give him a big hand. Thank you, Professor Schekman. Thank you, Mr. Gopal. Thank you, Professor Kulkarni. And now a few words from Professor Kartish.
So when I think about the journey of my parents, from my mother, Rajeswari Manthiram, who was the first woman in her family to go to college, when no one else had even gone to middle school, who used her training in mathematics to become a successful day trader. For my father, Aramuga Manthiram, whose own father passed away when he was just a few months old, was written off by everyone in the village, but who went on to earn a PhD to become a professor at the University of Texas at Austin, when no one else from his village had even finished high school. I know that I am living an unlikely life only because of the hard work and determination of my parents. I'm also thankful to my sister Kalpana, my akka, who at a very young age taught me everything about the world. She had a beautiful way of bringing meaning. She sat me down with all my teddy bears and she would just teach and teach and teach and teach. So she had this beautiful way of making learning very interesting. To my wife, Amrita, a bubbly entrepreneur who is the polar opposite of who I am. Those of you who meet her will see that. We're so different, but for this reason, she completes me. And that's something that I didn't know at a younger age would be what I would look for in a partner. To my daughters, Avni and Mira, who are joyful, who are compassionate, who bring curiosity and determination to everything that they do. To my in-laws, Anil and Ranjani Saigal, who are so supportive, have been there with us at every step. To our friends, Mohit Rajani and Sania Gurnani, who are like family. They blur that boundary. So we're so thankful. Hari as well from Chevron, who is here. I've known him since my MIT days, so I'm very thankful to have him here as well. To my students and postdocs who have worked tirelessly with creativity, with vision, to solve difficult problems in electrifying and decarbonizing chemical manufacturing. To the Infosys founders, conviction that science can lead to the betterment of society. That's something that we need more of. To the jury, for spending so much time to understand our work, right? To read the papers, to find the hidden meaning. The reasons why we place every period where we do, to see all that. We appreciate it. And finally, to the dynamic team at the Infosys Science Foundation. They have worked day and night, taking every phone call that we have to bring us all together here, right? This is remarkable. I didn't think this is where I'd be spending my January. But we're going to be thinking about remembering and talking about this day for years to come. So a big thank you to the team at the Infosys Science Foundation, the amazing staff there. Thank you.
Thank you, Professor. Thank you. The Gita reminds us the harmony of the world depends on the harmony of our actions. When we honor the cycles of nature, nature in turn sustains us. Well, ladies and gentlemen and friends, those were our 6 Infosys Prize laureates. Let's give them another big round of applause. And may I request Mr. Dinesh to lead our chief guest to their seats in the first row. Thank you, Professor Schekman. Thank you, Mr. Dinesh. Albert Einstein once said about playing his violin, I often think in music. I live my daydreams in music. And so to help you reflect on our celebration of high-quality research tonight, we are privileged to have with us Sri Ambi Subramaniam. He's hailed as the new king of Indian classical violin, and he's been trained by his father and guru, Dr. L. Subramaniam, and I was a big fan of him, since he was 3 years old, and he gave his first stage performance at the age of 7. He's performed across the world and was named among GQ's 25 most influential young Indians in 2021. And along with his sister, Bindu, he runs Sapa, which teaches music to over 40,000 children. He has co-authored over 30 textbooks, including India's first series dedicated to teaching the Carnatic violin. He's a youth delegate at the United Nations for the Sri Chinmoy Peace Meditation Group. He has a PhD in developing global violin technique, an MPhil in music, an MBA in finance, and a licentiate in the Western violin from the Trinity College of Music, London. Ladies and gentlemen, we present Ambi Subramaniam, joined by his team, Frijo Francis on keyboards and Karthik Mani on percussion.
Before we start, I'd just like to say it's very, very humbling to be in the same room as all of you. I think we love these kind of events because we learn so much standing there and listening to everything backstage. So very, very happy to be here and humbled really. We'd like to do two pieces. One, we'd like to do a Carnatic piece to start off with called Sri Chakra Raja. Thank you. Thank you so much. The last piece we'd like to play for you is another composition of my father's. It's called Peacock.
Tam kita taka tari kita taka tate tam kita taka tari kita taka de tam kita taka tari kita taka taka dimi takita tam taka dimi takita taka dimi takita tam taka dimi takita taka dimi takita taka dimi takita di tam kita tari kita tam kita tari kita tam kita tari Bitaka jano taka dim bitaka jano taka dim bitaka jano taka dim bitaka jano taka dim bitaka jano tam taka dim bitaka jano tam taka dim bitaka jano taka dim bitaka jano tam taka dim bitaka jano tam taka dim bitaka jano taka dim bitaka jano tam taka dim bitaka jano tam taka dim bitaka jano tam.
the new king of Indian classical violin, Ambi Subramaniam, with Frijo Francis and Karthik Bani. Let's give them another big hand. Thank you. And now I invite Mr. Chris Gopalakrishnan, co-founder of Infosys and trustee of the Infosys Science Foundation, to introduce our chief guest.
Ladies and gentlemen, it's a distinct honor to introduce our chief guest of the day, a scientist whose work has fundamentally reshaped our understanding of the living cell. Dr. Randy Schekman is a professor in the Department of Molecular and Cell Biology at the University of California, Berkeley, and an investigator at the Howard Hughes Medical Institute. His journey in high-level bioscience began in Stanford, where he studied the enzymology of DNA replication under Nobel Laureate Arthur Kornberg. However, it was during his postdoctoral tenure with S.J. Sanger at UC San Diego that he developed the fascination with cellular membranes that would define his career. Dr. Schekman shares a connection to India through his partner, Sabiha Merchant, who is here, who is a professor and Warren C. Evelyn Endowed Chair in the Biological Sciences at University of California, Berkeley. She's an elected member of the National Academy of Sciences and was also a juror for the Infosys Prize in Life Sciences in 2017. Dr. Schekman is known for his pioneering investigation into the mechanism of vesicular traffic in the secretory pathway of eukaryotic cells. By identifying the genes and mechanisms that govern how proteins are packaged and transported, he unlocked a traffic system essential to all complex life. For his monumental work, he has been recognized with the world's most prestigious honors, including the Gairdner International Award, the Albert Lasker Award in Basic Medical Research, and of course, the Nobel Prize in Physiology or Medicine, which he shared with James Rothman and Thomas Sudoff. Beyond the lab, Dr. Schekman has been a titan in scientific publishing, serving as editor-in-chief for both the Proceedings of National Academy of Sciences and eLife. Today, he's applying his expertise to one of the great medical challenges of our time. Since 2018, he has served as the scientific director of Aligning Science Across Parkinson's Disease. This major philanthropic initiative, in partnership with the Michael J. Fox Foundation, seeks to uncover the molecular mechanisms behind the initiation and progression of Parkinson's disease. Specifically, his lab is investigating how the release of proteins into alpha-synuclein may relate to the spread of pathology in the brain. Please joining in welcoming a visionary researcher and the leader in the global scientific community, Dr. Randy Schekman. I request Dr. Schekman to deliver his address.
Well, thank you very much for the generous introduction. It is my privilege to share the stage with our honored young scholars of science and language. I have a connection to Indian science and culture through my life partner, Savia Merchant. This evening I'm going to share with you the excitement in two developments relating to the march of molecular biology in our quest to understand genes. I will lead the way to the most recent breakthroughs in genome editing that have been accomplished by many scientists, including my own colleague, Dr. Jennifer Doudna. Although that promises such great opportunities in treating genetic diseases, we are now also faced with an emerging and largely unsolved problem of the march of neurodegenerative disease in the world. And I'll share with you my own efforts to try to help to break the logjam in that problem. Well, let's begin with the great discovery of the structure of DNA that was a milestone in 1953 by these two gentlemen, Watson and Crick, with some vital assistance by Rosalind Franklin, also in London at the time. We realized from their insights and from Franklin's crystallographic structure of DNA that the two strands of DNA can interact by a base pairing mechanism that immediately allowed us to understand how the gene could be perpetuated through life and through evolution. This was a truly monumental discovery. It followed nearly 100 years of discovery prior to that, first in the 19th century with the discovery of DNA itself by a German chemist by the name of Friedrich Miescher, who found this structure in the nucleus of cells, and since it had such a simple chemical composition, for many decades it was believed not to have any role in the transmission of genetic information. It took until the mid-1940s to understand that DNA is the seat of information transfer. It is the blueprint that cells use to convey information from one generation to another. Its structure launched a revolution in molecular biology that has led to a deeper understanding of how this blueprint can be realized, how it can be appreciated by the cells in our body, indeed of all organisms on Earth. These are the human chromosomes that we see here in color codes that are displayed from a cell that is caught in the act of cell division. We can now use the visual inspection of each of these 23 chromosome pairs to detect and to diagnose gross genetic abnormalities. But it took much additional molecular biology work to be able to sequence a gene in order to find the precise point mutations that are the basis of many of the genetic diseases. And now we are at the threshold of discoveries that allow individual mutations to be corrected by the modern approaches of genome editing. Just a primer for those of you who don't remember this from high school biology, but DNA is housed in the nucleus of our cells. It is decoded by an enzyme that makes an RNA copy of one of the two strands of DNA, and that message, that transcript, is conveyed from the nucleus into the cytoplasm of the cell, where it is then recognized by a machine, a ribosome, that stitches amino acids one next to another to make long polypeptide chains. These polypeptides can be thousands of amino acids long, and we've known for over 50 years that it is the physical chemistry of the interactions of the side chains of each of the 20 amino acids in a polypeptide and the backbone that allows a polypeptide to fold into a unique three-dimensional structure. It's taken scientists using a technique called protein crystallography to deduce the structure of thousands of such protein molecules so that we can understand, appreciate, and investigate the role of these polypeptides. But it was only within the last 10 years that it became possible, using AI, to devise programs, a program called AlphaFold, developed by a company in London named DeepMind, that has been successful in predicting the structure of all protein molecules that ever existed on Earth. Several years ago, they deposited online the predicted structure of 250 million different protein molecules. And scientists now can use this information to do experiments to test the function of proteins. On the other hand, it's also been possible through other investigations to create novel proteins that have never existed in nature, to create them for chemical, pharmaceutical, and technological progress. The discoverers of these programs shared the Nobel Prize in Chemistry last year. Now here is a polypeptide chain. It's a simple one. It starts with an amino acid at one end and is stitched together to make by peptide bonds to make a polypeptide that can grow to great length. Now I'm going to share with you another development that has been long in the making, and that is to understand how cells can react to their environment, in this case, to an arms race that has gone on for over 3 billion years on Earth. You may not appreciate it, but the most abundant particle of life on Earth is the bacterial virus. Every milliliter of seawater has 1 million bacteria, but has 10 million bacterial viruses. Bacteria and their viruses have been in mortal combat over 3 billion years and have evolved mechanisms to evade each other's defense systems. One of those systems you certainly have heard about, and that is a technology that is developed based on the structure of sequences in the genome, CRISPR sequences that can be recognized and can be used to code for small pieces of RNA that interact with an enzyme that chops DNA in a very sequence-specific manner. Now, I want to share with you a video that was done for my colleague Jennifer Doudna on the next slide that describes briefly how this technology works.
Scientists have long imagined being able to make specific changes to the genetic code of a cell or organism. A revolutionary genome editing technology invented by scientists at UC Berkeley and Umea University makes this possible using an RNA-guided protein called Cas9. Cas9 searches through the cell's vast genetic material until it finds a sequence of DNA that matches the sequence of its programmable guide RNA. The guide RNA enables Cas9 to open the DNA helix and to position 2 molecular blades to cut each strand of the DNA double helix. Repair enzymes seal the gap in the broken DNA, sometimes by inserting new genetic information supplied by the cell or the experimenter. In this way, disease-causing mutations can be corrected by changing the underlying genetic code. Scientists are now using Cas9 technology for research applications in human health, agriculture, and bioenergy.
Now I want to share with you the breakthrough from just 3 or 4 years ago that has allowed this technology to be harnessed to cure a disease endemic in Africa called sickle cell anemia. Now, many of you know that the oxygen in our blood is carried on a heme-bound protein called hemoglobin. Hemoglobin has 4 protein subunits coded by 2 different genes. It is contained within these biconcave red blood cells. Oxygen is collected by binding to the iron on hemoglobin when blood cells pass through the lungs, in arteries through the lungs, and they convey that oxygen to peripheral tissues where the low oxygen tension causes the oxygen molecule to step off the hemoglobin protein one at a time and to go into tissues to sustain oxidative metabolism. Now that works very well in most of us, but patients with a rare mutation in one of the globin genes that you can see on the very left, on the top are the first 7 amino acids, the top left, the first 7 amino acids in one of the beta globin proteins, and on the bottom there's a change at amino acid position number 6. This one substitution is enough to cause a critical change in the structure of hemoglobin. This change was discovered by the greatest chemist of the 20th century, Linus Pauling, who predicted the existence of the genetic basis of disease, and he had postdocs in his lab prove that by demonstrating that globin isolated from sickle cell patients had a different electrophoretic property than normal globin. Now what happens in the red blood cells that carry sickle cell globin is that when oxygen is picked up in the lungs and conveyed to peripheral tissues, when the oxygen is released, the globin, rather than remaining a soluble protein, forms a long, rigid fiber, as you see in the lower right. And that can extend through the length of a red blood cell, causing it to rupture and to release hemoglobin into blood. This causes very severe anemia and is a terrible progressive disease in patients who have 2 bad mutations in both copies of the gene. Now, just several years ago, it became possible using CRISPR technology to make a subtle change in the genome of patients with sickle cell anemia to unleash the expression of a gene of globin that is normally only produced in the fetus. And now, with that expression, patients who had sickle cell anemia survive quite nicely because they rely on fetal hemoglobin as opposed to the mutant adult globin. That was the first and most dramatic achievement with the CRISPR technology, but just in the past year, another even more dramatic development has happened that allowed a team of investigators to precisely change a mutation in a young child, only 3 months old, who would have died within the next few months had that mutation not been corrected to change, to repair a metabolic disorder. So this heroic effort led to the curing of a genetic disease in this one child, and it shows promise of being able to do so for all such genetic disease in the future. This is a tremendous breakthrough. Now, I go from a tremendous breakthrough to something that is rather more problematic and for which there has been no solution and is growing in severity around the world. And that is the basis of neurodegenerative disease. The brain is the great frontier in biology. The brain has tens of billions of cells. Each cell can make hundreds, indeed millions of connections to other cells. That is, we have trillions of different nerve terminals in the brain informing all processes of thought and emotion. Everything about us is dictated by the selective communication between nerve cells at nerve terminals. Some of these nerve cells die, and as they die, one progressively loses cognitive function. The most severe forms of cognitive loss, cognitive dysfunction in the world are Alzheimer's disease and Parkinson's disease. But it turns out, for reasons that are not well understood, that Parkinson's disease is rising at a greater rate than Alzheimer's disease and threatens to take over many more people around the world. It is a challenge around the world. It shows it's like a pandemic. It obeys no boundaries. It's estimated that in the next decade, China will have over half of the new cases of Parkinson's disease diagnosed in its people, and it's not simply because of better diagnosis. It may be because of environmental toxins. We know from genetic studies that there are 20 different genes, mutations in which cause familial forms of Parkinson's disease, but even those are only a minor fraction of all of the Parkinson's patients around the world. It's likely that 80% of Parkinson patients arise by some sporadic process, which I'm guessing is going to turn out to be some environmental toxin. China may be particularly bad in controlling those toxins, but other countries will be severely affected. Now, I'm going to share with you a few observations that have been known now for many years that explain at a kind of a crude level what happens in a Parkinson patient. When a Parkinson patient first presents with the movement disorder, it's estimated that over half of a set of cells in the brain called the dopaminergic neurons that congregate in the midbrain section called the substantia nigra have died. That can be seen visually in the brain sections through the midbrain region in my diagram on the left. The sample labeled C is of the patient who died for other reasons, and this dark band of cells represents the dopaminergic neurons in the substantia nigra that ultimately produce an oxidized form of dopamine that creates the pigment melanin that we know that's responsible for skin color, but this pigment is also present deep in our midbrain and can be seen without staining in the sections as you see here. A patient who died as a result of Parkinson's, as you see on the left, has lost almost all of those dopaminergic neurons, and this proceeds more rapidly than normal, although we are all suffering as we grow older with the loss of these cells, because you'll see in a moment how vulnerable those cells are to almost any stress. On the right is a section of the midbrain that was seen now 100 years ago by a German clinician by the name of Frederick Louis, who found in the dopaminergic neurons in patients with Parkinson's a kind of a clustering of dense material, stained kind of red here in this image, a clustering that is now known as the Lewy body, and it correlates with the progression of the disease. It has only become possible recently to be able to see these in the brain of a living patient with a very powerful and sensitive PET probe. But until now, we could only see these Lewy bodies in sections of deceased patients. Now, one of the proteins that is coded by one of the 20 genes that is known to cause Parkinson's is the gene for alpha-synuclein, and its protein product is shown in a little stick diagram at the bottom. It's a small protein. It's a brain-specific, relatively floppy, unstructured protein. The genetic forms of the disease in this gene are of two types. They are point mutations, such as you see highlighted in red in the beginning part of the protein. Those are in familial forms of Parkinson's. Another is a rarer genetic change that involves the genome acquiring 3 copies of the same gene. Thus, the protein becomes overexpressed. It's more abundant in nerve cells as a result of either a mutation or of its abundance. This protein tends to aggregate, and its aggregation appears to be the basis of the formation of a Lewy body. So one of the challenges is to try to reduce the expression of this gene or to cause the brain cells to degrade the aggregates. That is a major challenge that we face. Now, more recently, another German clinician, Dr. Brock, sectioning many brains of patients who died at different stages in Parkinson's disease, observed a progression beginning on the left, as you see, with a few Lewy bodies that can be seen at the brainstem. And interestingly, Lewy bodies in the olfactory bulb. Now, this is interesting because many patients who progress to Parkinson's report that they have a poorly developed sense of smell. This phenomenon can persist for years before the disease is manifest. As the disease progresses, these Lewy bodies can be seen elsewhere, not only in the substantia nigra, but also in the brain cortex. And many patients, perhaps even a majority of them, eventually succumb to a form of dementia as a result of these lesions that are spread now all over the brain and not just in the dopaminergic neurons of the substantia nigra. Now, the alpha-synuclein is just one part of a very complex story. There are many other genes that are involved in this disease, genes that operate in many of the other cells in our body. So why do these genes, when mutated, affect dopaminergic neurons so selectively? Well, one piece of evidence for this is the enormous complexity of the dopaminergic neuron itself. So here's an example. Many of you may have a visual impression of what a nerve cell looks like. It has a cell body and it has tendrils pointing in other directions, making connections to other nerve cells. But the dopaminergic neuron is so complicated, it has a forest of nerve terminals numbering close to 1 million, making connections to another tissue some centimeters away called the striatum. And it is that connection, that communication between dopaminergic neurons and cells in the striatum that perform all of the functions, executive function, movement functions that we know are compromised in patients with Parkinson's. These cells are poised on the edge of death. They must survive. They must sustain themselves by energy production, and any little insult is likely to propel them over the boundary into death. Now, why have I become involved in this? Why am I telling you this story? My own work relates peripherally to this, but I have a more personal connection to Parkinson's, and that is my wife of 44 years, Nancy Walls, became ill with Parkinson's when she was just 48 years old. Here's Nancy when we were happy and healthy. We had our children together in Berkeley and everything was fine. The children had grown. One of them was away in college, one in high school. When she suddenly presented with some very peculiar symptoms that couldn't be diagnosed, her neurologist said it could be Parkinson's. She said, well, how will I know? Well, you take a pill that is basically a replacement of dopamine. And I'll never forget the afternoon that she called in my office to report that having taken the pill, all of the symptoms were gone. Within 2 hours, all of the symptoms melted away. This was the good and the bad news. But we soldiered on because it could be controlled. At this stage, early on in the disease, within 5 years of diagnosis, it can be relatively stabilized and controlled by the administration of drugs. As the disease advances, even partly in response to the drugs, patients start to develop dyskinetic movements, these awkward movements that are associated with the motor dysfunction. But that too can be corrected, and she had a procedure called deep brain stimulation, where 2 electrodes are implanted bilaterally into the midbrain to control a region of the brain that responds to the motor executive functions of the substantia nigra. This worked really well for her. She lost some of the aches and pains that she had, and her movement was restored. But unfortunately, within a year, she started to develop symptoms of dementia. She was a nurse by training, and she knew what this meant. When dementia sets in, it doesn't reverse. It only gets worse. And she did. She lost many of her functions, but we still soldiered on. There were happy moments. Here is a picture of Nancy and my father at the Nobel ceremony in 2013. She suffered from dementia quite seriously at this point, and she had to be sustained and nurtured by my family members who were with me on this special occasion. But as we got onto the plane to return to California, she came back from the bathroom and said, I was talking to somebody before I went to the bathroom, and I forgot where we were. What was it that we were just doing? We had just returned from the Nobel event. It only got worse. As time went on, she lost her ability to communicate. Because she would forget what she wanted to say, she became incontinent. It became very difficult to manage her symptoms. I had access to the best neurologists in the world, particularly with her specific form of Parkinson's, which was referred to as diffuse Lewy body disease. I would always ask, what can I do to prepare myself for the next? Because I know there wasn't anything I could do to help her. How could I, make it easier for her to sustain her? They always had an answer, and they were always wrong. Here she is, just a few months before she died. She was catatonic much of the day. I had difficulty giving her medications. She required full-time care. She had pathologically low blood pressure, so she would fall and hit her head. It became almost impossible to manage. And then one evening, in the middle of the night, she died. Her general physician called me the next day to say, well, she thought Nancy had a severe loss of oxygen perfusion to her heart muscle. No one ever told me. This is the frustration of people who care for those who have these serious disorders. There's no way to prepare. But out of this came something quite miraculous, and that is, I was asked by the chief financial officer of the Sergey Brin Family Foundation if I would help develop an international program of basic research on Parkinson's. This was because Mr. Brin, the co-founder of Google, enormously wealthy, has a family genetic history of Parkinson's. He and his mother share a mutation in another gene that I haven't told you about. His mother is ill with quite advanced Parkinson's. He is now asymptomatic, but he has a vested interest in pushing this forward, and so he decided by himself that what we really needed was a focus on the basic science of Parkinson's. So I was thrilled to be given this opportunity to take this on, and for the past 7 years, we have focused on funding teams of investigators, not individual investigators, but teams who collaborate for common purpose. Academic science is wonderful. Our award winners today have all enjoyed the benefits of academic science. But there is a challenge in academic science, and that is the reward structure favors the individual, such as we see displayed in the front row. But real progress on complicated problems like Parkinson takes a team effort, and the team, the collaborative effort is not necessarily well supported by our current grant system. So my partners and I in this effort decided to really focus on teams and to reward teams who really share all of their information. They share reagents, they share protocols in real time, not only when they're published. We have focused on 4 themes over the years. One is the genes and their associated proteins. Another is the immune system, the body's immune system and the brain's equivalent that may influence the progression of the lesion. Another is to simply find out, try to map the circuitry of this complicated dopaminergic neuron. And finally, to try to understand the very peculiar precursor symptoms. I mentioned one, a progressive and loss of smell. My wife suffered from this when we first met. She didn't have a well-developed sense of smell. It is very common to then proceed to Parkinson's disease. Another one that is a more certain connection is a syndrome called REM sleep disorder, where patients report that they lose their ability to control their movements during sleep. They often throw themselves out of bed, or they start fighting with their partner, unconsciously fighting. This is very frightening disease. It's called REM sleep disorder. Within 5 years, 80% of those people progress to Parkinson's. We don't know why. Well, let me give you a snapshot of where we stood a few years ago. At its peak, we identified 35 teams, 163 laboratories around the world, well-balanced team with early career investigators, many women leading these efforts. The funds were distributed to 80 different institutions in 14 countries around the world. We have now committed actually over $1 billion. Mr. Brin is enormously generous in not looking over our shoulder and just letting us do what we want. And finally, although most of our work is conducted online and sharing information, we have annual meetings. The first such annual meeting was in the Bahamas, as you see on the right. All of the team leaders are displayed here, and in the front row I'm standing next to my partner in this effort, Kemeny Riley, and to the leadership of the Michael J. Fox Foundation, with whom we work hand in hand in this quest. We have 5 more years of this program. We have breakthroughs that have identified targets that I am confident the pharmaceutical industry will embrace in finding cures that are more effective. And when I walk away from this program in 5 years, I will leave behind, with some confidence, breakthroughs that will make a difference in the lives of those afflicted with this disease. Thank you for your attention.
Thank you, Professor Schekman, for those fascinating insights and that very deeply personal story, telling us about the tremendous breakthroughs that have been made, but also how much more there is to do. Well, as we draw this evening's program to a close, I now request Mr. Salil Parekh, CEO and MD of Infosys and trustee of the Infosys Science Foundation, to deliver a vote of thanks.
So good evening, everyone. That was absolutely inspiring and humbling, Dr. Schekman. So thank you for sharing such a personal journey with all of us today. So it's been an absolute pleasure to be with all of you for this incredible Infosys Prize event. It's really fantastic to celebrate the individuals that have been awarded the Infosys Prize this year. As always, inspiring to hear their stories, incredible to see the type of work done, from market design to linguistics to maximum flow, something new that I've certainly learned today, to using sunlight and water for making fertilizer. The Infosys Prize Award winners have done exceptional work, and it's amazing to see that all of that can be shared with us and broadly to help what all of us can do going ahead. A sincere thanks to the jury members and the jury chairs for really identifying and selecting the Infosys Prize awardees, to dig into all of the work that's been done across many, many different people, and to identify these individuals here in the work for the award of the Infosys Prize. The past year has seen amazing progress. Dr. Schekman, in fact, mentioned about gene editing. We've seen some incredible work on quantum computing, especially in the area of large qubit systems. Those are inspirations where we think what the Infosys Prize awardees have done will lead to such new and breakthrough discoveries in the future as well. It's truly exceptional honor for us to have as our chief guest Nobel laureate Randy Schekman. What he shared, as I mentioned earlier, was an incredible personal journey, but a phenomenal approach to doing research and making an impact, and an ability to share that with all of us to explain things in a way that we could relate to our limited biology knowledge. A sincere thanks to the government of India for investing in the future of our country and making the prize money for the awardees of the Infosys Prize tax-free in India. Thank you to the trustees of the Infosys Science Foundation for their incredible vision and foresight in instituting this prize. One can see every year how such a prize makes a difference in both rewarding what is going on, but inspiring the future generations who will see this and continue with their work even as they go through many challenges that we face. Infosys, the company, is also proud to support everything in the mission of the Infosys Science Foundation. The work that they do in recognizing this and then inspiring more and more awardees is incredible. Thank you to the Infosys Science Foundation team led by Bhavna, all the Infosys team members who helped make this event so special, and to Deepak for guiding us through this evening. And thank you again for all of you for joining us, and look forward to the evening celebration.
Thank you, Mr. Parekh. And a special shout out also to the Infosys Communication Design Group, who work very closely with the Science Foundation to present all those lovely videos and all these amazing graphics. Big shout out to them. Well, to continue those moments of gratitude, I now call upon Mr. Narayana Murthy to honor our chief guest with a token of our appreciation. Mr. Murthy, and ladies and gentlemen, please put your hands together in thanks to Professor Randy Schekman. Mr. Murthy and Professor Schekman, I request you to stay on the stage as I now call our jury chairs to receive a token of appreciation from Mr. Murthy. Professor Kaushik Basu. Professor Jayati Murthy. Professor Akhil Bilgrami. Professor Mriganka Sur. Professor Chandrasekhar Khare. And Professor Srinivas Kulkarni. May I request Mr. Dinesh to join us on stage for a group photograph of the jury chairs and Professor Schekman. Jury chairs, Mr. Dinesh, Mr. Murthy, Dr. Schekman, if you could stay on stage, and while I call upon our winners to join us on stage with your certificates, if you can. Just give them a moment. you recall what Professor Kare said a little earlier about weather systems being chaotic, dynamical systems, we have a bit of inclement weather outside, and so dinner tonight will be at the ballroom. The ballroom is at the start of the pathway that led you here. And with that, let me say thank you to all of you for sharing this very special evening with us. And we'll see you next year. Thank you.